time-of-flight mass spectrometry is one of those topics that sounds way scarier than it actually is. And once you get your head around the sequence of steps, it's honestly pretty satisfying. In this video, we're going to break down exactly how a time-of-flight mass spectrometer works step by step. We'll look at ionization, acceleration, the flight tube, detection, and along the way, I'll flag the most common exam slip-ups students make and show you how to avoid them. And if you stick around to the end, I'll also run you through a couple of classic past paper questions so you can see how all this theory lands in an actual exam scenario. Let's dive in.
Let's start with what time-of-flight mass spectrometry is for. It is a tool for analysis, and what we use it for is to find out the mass of different elements and compounds. So for example, we can find the abundance, meaning how much, and the mass of each isotope in an element. Now remember that word isotope, it means same number of protons and different number of neutrons. For example, chlorine 35 and chlorine 37. And if we know how much of each isotope we have and the mass of each isotope, we can determine the relative atomic mass. If we are analysing a molecule, then we can use time-of-flight mass spec in order to find out the relative molecular mass. There are 4 stages to something that we analyse with time-of-flight mass spec. The first thing we do is we take our substance and we ionise it so everything is 1+ ions. We then accelerate them so they all have the same kinetic energy. Then they travel a fixed distance in a flight tube and then they're detected at the detector. We're going to dive into each of these stages one by one. So the first stage is ionisation, and there are 2 different methods depending on what it is we are analysing. Now, why do we need to ionise everything? We need to create 1+ ions so that we can accelerate them, separate them, and then detect them. So it's a crucial start of this process. Now, the first method for ionisation is something called electron impact. It does have another name, you might come across it as electron ionization. Now, we use electron impact as a technique when we are working with atoms or small molecules. The way that we do it is we first of all turn our sample into a vapor, into a gas, and then we fire higher energy electrons at it. And that knocks off 1 electron from each particle, and that creates a 1+ ion. That is usually written as an equation like as shown. So that is X, whatever that atom is as a gas, goes to form X plus, also as a gas, plus the electron that you knocked off. Then that 1+ ion can be attracted and then accelerated. This is what it looks a little bit like to help you get a firmer grasp on what's going on here. So on the left-hand side there, that's where our gas sample is. It's what we put in, what we are analysing, and we've turned it into a gas. That then passes along or through this electron gun, which is firing these high energy electrons at it. And when they collide, they knock an electron off. So remember, this technique is used for elements and small molecules. When we ionise in this way, via electron impact, then what we are producing, that 1+ ion, is known as something called the molecular ion. The molecular ion can also sometimes break down into smaller fragments. So it means in a second when we look at a mass spectrum, you will have a peak where the molecular ion is, and then it's possible that you have smaller peaks further along, and those might be the fragments of that molecular ion. Now, electrospray ionisation is the second way that we can ionise. So we're still in this first stage of the time-of-flight mass spec process. So electrospray ionisation is used for bigger molecules. So for example, proteins, where the MR is many, many hundreds. So what we do in order to turn these into ions is first of all, you dissolve your sample into what is known as a volatile solvent. So a solvent is just something that we dissolve something into. Volatile means low boiling point, i.e. easily turned into a gas. And of course, that's the state that we want in our time-of-flight mass spec tube, because if everything is a gas, it can move around. And if it can move around, and it's ionized, we can separate it. So we've dissolved it in our volatile solvent. We then inject it through a fine hypodermic needle. And what we do to the tip of that needle is we put a high voltage across it. That means that each one of those molecules are gaining a proton. Now, a proton is a hydrogen ion, an H+ ion. And just to link those two ideas up together in your brain, if you haven't come across this before, a hydrogen atom, element number 1, is 1 proton and 1 electron. So to become a hydrogen ion, it loses that 1 electron to become a H+ ion, which is just a proton. So the two here are interchangeable. A H+ ion is 1 proton. And that means our molecular ion becomes whatever our sample was, X, with that H+ attached onto it. And that's where the 1+ charge comes from. Again, this is what it looks like, or you can visualize it as. So we have dissolved our sample in our volatile solvent. It's then pushed through that hypodermic needle, and that's where the high voltage is applied. Each one of those molecules then gain that proton, and that's then entering as a gas into our time of flight mass spec tube. And this is how we'd write this as an ionization equation. So this time, remember, we're adding a proton on. So you're going to take your X, your large molecule as a gas, and add the H+ ion on. That's going to make X, whatever our sample was, plus that H+ ion. And you could combine that into a molecular formula. So completely fictitious here. If we had C18H34O, then that would become C18H35O+. So you're adding that hydrogen ion on into the molecular formula. The next stage, stage 2, is acceleration. Now we do that using an electric field, meaning every single ion that's in there has the same kinetic energy. And that means the velocity, the speed of each of those ions, depends on its mass. So lighter ions have a faster velocity, i.e. if you are lighter, you travel faster, you are quicker. A heavier ion will have a slower velocity, so it will travel slower and take more time to go down that time of flight tube. This is the equation, and in the next video I'm going to show you a little bit more about how to use this equation in exam questions. So make sure you tune into that one, hit subscribe now so that you get notifications for the new videos every week. So our equation, kinetic energy of the particle, that is in joules. And then there's a couple of places they can catch you out here in terms of the units. So M is the mass of the particle, mass of one particle, which we don't often do in chemistry. Usually we work with moles of particles, right? The mass of one particle, and that's in kilograms. So there's some extra manipulations here with the calculations we're going to need to do. Again, tune into the next video if you're like, that's confusing. And then V is velocity. If you want to rearrange this, then you can see that V equals the square root of 2 times the kinetic energy divided by the mass. The next stage, stage 3, is a flight tube. So the flight tube, we now have our positive ions, and they all now have the same kinetic energy, having gone through the first 2 processes. They then travel through a hole in this negatively charged plate into a fixed distance, which is the tube within the mass spec. Remember, those lighter ions travel faster, so they take less time, they have a shorter time of flight than the larger, heavier particles that are moving much slower, and they have a longer time of flight. So an example there are the magnesium isotopes. So the magnesium 24 plus ion, that will have the shortest time of flight because it has the lowest mass. And vice versa, the 26 magnesium ion is the heaviest one. It will travel slower and have the longest time of flight. This is what that looks like in practice. You can see there those magnesium ions, 24, 25, 26. 24 ion, the 24 magnesium plus ion, is going to reach the detector faster in a shorter amount of time. Then the final stage is detection. So detection happens when these positive ions have reached the end of the tube and they are hitting a negatively charged electric plate. When they do that, those ions are gaining electrons from the plate, meaning therefore we generate a current, and it's the current that is being measured. It's the current, the size of the current, that gives us the number, the abundance of ions hitting the plate. So we get two bits of information here, remember. We get the mass, and we also get how much, the abundance of each sample. And that's to do with the size of the current that's generated at this detection plate. So we've now done our 4 processes. Our time of flight mass spec is complete. We now get a mass spectrum, a printout, a readout, a graph that we can now use to analyze our compound or our element. Now, along the x-axis, you have what is called the mass to charge ratio, mass divided by charge. Given that, remember, we ionize everything into a 1 plus ion, then mass divided by +1 is equal to the mass. So effectively, if we're using an electron impact method, then the mass to charge ratio is the mass of each ion. I'll say that again. Because the charge during ionization is +1, we've engineered the conditions so that we get the majority of 1 plus ions. Mass divided by that +1 means that the mass to charge ratio is effectively the same as the mass if we are using electron impact. And this is what that looks like. So using those magnesium ion example again. So you can see there along the bottom that we have 3 peaks. So we have 3 ions present at 24, 25, and 26. Because 24 divided by 1 plus 1 is 24, then that means that mass to charge ratio is the same as the mass of that ion. We can also see the abundance of these. So that is the y-axis, remember, and we can see here, for instance, that the 24 magnesium plus ion, we have 79% of that compared to much less of the others. Now, remembering what the point of all of this was, why do we want to do this in the first place? It's because usually we're trying to find out the relative atomic mass or the relative molecular mass of something. Now, in this magnesium ion example, we can find out the relative atomic mass. And the way that we do that is we find the combined mass of all of the isotopes and the combined abundance for all of the isotopes. So the data there that you can see, that is read directly off the mass spectrum on the previous slide. So we do 79, that is the abundance of the 24 magnesium ion. We add that to the 10, which is the abundance of the 25 magnesium ion. And then we add that to the 11%, how much we had of the 26 magnesium ion. That's the combined mass of all of those isotopes. We then divide that by the combined abundance. So that's 79, 10, and 11%. That is how much we have in total of all of the isotopes. And that gives us our overall answer. Usually it's to 1, maybe 2 decimal places. Make sure you read your question carefully in an exam so that you don't slip up there. And how nice would it be if that was the end of the story? But there are a few places we can also now be tripped up upon. So we also need to be careful of other peaks that might be around that molecular ion peak. So remember, the molecular ion is the mass of the overall ion. We can have small peaks either side of that, usually because we have different isotopes present. So here's an example of what I mean. So this is a mass spectrum for propane. Now the peak with the highest mass to charge ratio, so look all the way to the right-hand side there, is 44. And that tells us the overall mass of the propane, the molecular mass, relative molecular mass, that's 44. You can see there, though, there are lots of other peaks there. So what are they about? Well, the ones much further down, they're going to be fragments, little bits of that molecular ion. The ones that are like above or below shifted up by 1, so for example, the peak at 45, That's because usually just naturally occurring, we have different isotopes of hydrogen and carbon that are much less common than your normal isotopes of hydrogen and carbon. So we can have an isotope of carbon that is 2 hydrogen or 13 carbon. And usually if you see a small peak that is 1 up from the molecular ion peak, it's because we have a hydrogen 2 or a carbon 13 in that structure. Now, it's a little bit different if we are or have used electrospray ionization in that first step. So if we have used electrospray ionization, remember we are adding a proton, a hydrogen ion, and that's how we are creating these 1+ ions. So if we look, for example, here at a protein, then you can see there is a peak at 521.1. That molecular ion is the mass of the molecule plus the proton that you added on. And a proton has a relative mass of 1. So it means we have to take that off again in order to find the relative molecular mass of the protein, which is therefore the 520.1. And then if we have even smaller peaks above that, so for instance, if we have 522.1, then that is again a substitution of an isotope such as carbon-13 or hydrogen-2. So we have covered a lot here in this video on mass spec, and there is more to come. So if you want to see some walkthroughs of some of the calculations they can give you in this topic, plus some extra little bits and common mistakes, then check out the next video in this series where I'm going to add on to what we've done here and give you some key examples. But what we've covered today is what mass spec is used for. It's an analysis tool for finding the relative mass of elements and compounds. We've covered the 4 different stages: ionization, acceleration, travel along the flight tube, and detection. I will see you next time, and thanks for joining us today.
Thanks for watching. Make sure you hit subscribe if this helped you so that you can access all of the new lessons that come out every single week. I'll see you in the next video.